Okay, so before this lecture, we spent 4 lectures to talk about GPU architecture, right? So this is a rather unconventional decision to make GPU architecture before the CPU architecture. We think, at least I think, GPU architecture is simpler in many aspects than CPU architecture is simpler on some other aspect. So we use a GPU to give you lots of preview that we touch a little bit on cache coherence, we touch a little bit on the instruction pipeline, so that we can give a preview for the rest of the semester. So we use CPU to dive deeper into the same topics again. So like as when we first talk about GPU architecture, we start with the software, the how to program a GPU, how to write a GPU program, and how the GPU assembly looks like. And with CPU part, I think all of you know how to write a CPU program, like a C program, a Python program. This type of program eventually compile into ISA. ISAs can be different from one to one, but the main idea are close to each other. So we use RISC-V ISA, which is like the most popular in academia today, as an example to talk about the CPU ISA, the CPU code. Then starting from there, in the next lecture, we talk about how the CPU core is designed with this type of, with specific to RISC-V ISA. Although the general idea works for all type of architectures, all type of ISAs, okay? So starting from instruction set architecture, now we consider the earlier programming. How earlier programming is done by this type of punching card programming. This is really early. Now later on, even with storing techniques, we write the program. But when people write a program, they write the program in a machine-specific way. So if you have one machine, write one program, then there's another machine. If your company decided to buy another machine, then you need to write all your code again. But pretty much at that time, there's no big concept of software reuse anyway. So how does it work is typically in the morning or in one day, you prepare all the punch cards that you really need to execute. Then you give the punch card to some like computer operator. Then they will take your card and feed into the computer. Then in the evening, you get a result. If the result is wrong, then you just have nothing to do. You just figure out what's the problem, and the next day you send another card to the operator, then they will execute it for you. So consider how hard it is to debug this type of code. Then, although the code are not likely to be very complex at that time. And the first system that brings the idea of ISA is the IBM 360 system in the year of 1964. And by that time, the goal is to deliver a family of machines. So they think, oh, we want to have just high-end machines for some big companies, lower-end machines for some smaller companies, or who is not very sensitive to performance. And by that time, how you can have one series or one family of machines covers different type of market, but you want the software to work on all of them. Then computer scientists or computer engineers, the best thing that they are good at is to think one way of indirection, right? They think they just introduce an abstraction layer so that they can make the whole idea works for different type of machines. So there are two layers of abstractions starting to get separated from this point. One is the architecture level, or sometimes it's called instruction set architecture level. Then this is a abstraction between the software and the hardware. It's the protocol between the software and hardware. If we encode the program in this way, then our software hardware will be responsible for you to get a result. But we cannot ensure you the performance, because the performance is done at the second layer, is to get a lower layer. It's called a microarchitecture level. So the microarchitecture level is responsible for the implementation. So for example, you may have a lower end with some lower end cores may not even have division module, right? So they can use some multiplication or add subtraction to mimic the division operation. Now it definitely will take longer time, but it allows the device to be cheaper, smaller die size. So there are different type of microarchitecture. Another example is today you might hear that on our phone or on our computer, there's a performance core and the low energy core, right? So they have different cores. So for most of the time, the low energy core is good enough for you to respond for your request. But when you really need high performance, when you are doing some computation heavy workload, you really need a performance core. Then this type of abstraction allow you to have different hardware to support the same program at a different performance. So by that time, we start to have the separation between instruction set architecture and the microarchitecture. Okay, so today we're going to mainly talk about one example of instruction set architecture. On the other side, now for the rest of this lecture, we're mainly talking about microarchitecture side. Okay, so one particular example is the journey of Apple computers. Then starting from in 2004, they started to use IBM PowerPC, right? Then after that, they started transit to Intel Core. And that was a very painful transition by that time. Then later on, they start to transit to ARM, to transit to the machines that they are really designed, the chip really designed by Apple. Then that's another very painful transition by that time. But Apple did it very well by that time. When Apple M1 is really used, immediately like, we can feel like experience improvement because the energy consumption is much lower and the design is much better than the Intel cores. Now, I don't know if you have used the Intel machines, Mac machines. It always make a noise. Then the battery probably lasts 2 or 3 hours, so that we always need to carry a power, the power cable. But with today's MacBook Pro, now almost I just use it. I don't need to bring a power cable with me. For most of the time, during daytime, this is good enough. Then, so if you consider this is already a very painful process. Now for Windows, if you know the journey of Windows, Windows have been starting the transition from x86 machines to ARM earlier than Apple. But even today, you probably won't really buy an ARM-based Windows machine because of the performance and because of the efficiency. So on another side, now if you look at the GPU, assembly, GPU ISA, then for NVIDIA, you have like when you hear about the architectures, the architecture, NVIDIA may have Fermi. These days we have Hopper, Blackwell, then those are generations. So different generations of GPUs, they all run at a different ISA. Then AMD also have this GFX8, GFX9, GFX10, like CDNA, RDNA, RDN1, RDN2, RDN3. These are all slightly different ISA. So why GPU is so easy to change an ISA and why Apple is rather easy to change an ISA, but Windows is so hard. Linux is also so hard to deal with the ISA transition. It's mainly because of the ecosystem is closed or open. For Windows or Linux, they really have an open ecosystem. That means the compiler is controlled by one group of people, software is controlled by another group of people, then the hardware is controlled by another group of people, operating system, another group of people, right? Then they need to work together. So one side, they change something, the other 3 parts also need to adapt to support new thing. Just consider if you one day change ISA, then all the software doesn't really compile. Then some software may just no longer have a maintainer. So nobody maintains the software, then nobody can simply recompile the software for your new ISA. And if they cannot recompile, then you cannot use the software. And compatibility is a big issue. Apple definitely controls the ecosystem more, but for GPU vendors like AMD, they control the compiler, they control the intermediate representation, they control the hardware and the assembly, they control everything. So that's why they can switch the programming, they can switch the ISA so quick that they do not really have to fix with one ISA design. Okay, it's just different type of ecosystems. Then you probably have heard of this term called CSCI and RISC. One is for complex instruction set, and RISC is reduced instruction set. So the CISC design is large and complex, and the RISC design is small and simple, right? So why CISC is so large and complex is because in early stage, your computer is not so complex. There are some simple, some style of instructions. For example, if you write add instruction, if you write add instruction, add two numbers together, you don't really have to deal with registers directly. If one piece of data is in the memory, no problem. You can just directly get from the memory. So in early days, in x86, we can have some instructions like this. R1, R2, then this one is R3. I'm just making it up, okay? So what does this mean is R1 and R2 are registers. R3 is a address, it's a memory. So we can load this piece of data from the memory that is represented by this address. The address is stored in the register. Then we load this piece of data, then perform add instructions and store it there. Okay, so this is a typical symbol of CISC instruction set. Then there are probably more opcodes, more type of instructions that they can support. You can combine multiple operations together. The RISC is designed in the other way because they want to be really simple. Why CISC is designed in this way? Because in early time, the memory is not that slow, or actually the core is not that fast. So the speed difference between the core and memory is not that large. So loading from a memory is not a big problem. So we can just load it while we're doing this calculation, not really slow. Today, our core is getting really, really fast. Then we cannot really use this type of representation here. So what we do is we add dedicated load instructions. We have load instructions. We load into R4 from the data that is represented in R3. Then we put R4 here. Okay, so we have more program. We have more instructions in our program to do the same thing, and each instruction is doing fewer things. Then typically this type of implementation is more friendly to today's faster cores. Now, because load is super slow, right? Last time we talked about latency hiding. Load is super slow. Now we need to put into special instructions so that we can put special consideration to this type of load and store instructions. And also today, the boundary between CISC and RISC are not that distinct. That it's really hard to tell if it's a RISC machine or a CISC machine. We all know that x86 is a CISC machine, right? x86, the Intel CPUs or AMD CPUs that we run is x86 ISA. Then, but it's actually a RISC under the shell of a CISC ISA. What it does is even sometimes you see this type of instruction. Sometimes you see this type of instruction. They use something called microcode. What is a microcode? It's basically an ISA that you don't see. They just use this x86 as an intermediate representation. Then they actually do what they do is they translate this type of instruction down to load and the add instruction. Okay, they convert it into multiple instructions. So they do smaller operations so that they can achieve the same level of performance as what RISC is doing. So this is what's happening internally at the Intel machine. Okay. So they still need to support CISC x86 ISA because of a compatibility issue. That's their burden from the history. Okay. So we talk about machine. Let's talk about machine languages. Then what machines is. Then machines can see this type of binary format or files, when you run an executable program, what they see is basically a file. Then the file is encoded in binary, right? Then this part is the binary representation of this instruction. It's the binary representation of these instructions. These are what your computer sees, like 0010293. These are representing hex numbers. Okay, those are something that your machine sees. Then typically we say there are two different formats. One is the binary format and one is the assembly format. Binary format is the machine language. Then assembly language is basically a human readable binary format. Then there's a one-to-one combination. And also if you look at here, this is a disassembled file. And disassembled file means we get this binary, then we convert it into the assemble language. And we can see, okay, this byte, this 4-byte, it represents ADDI instruction, integer add instruction. Okay, then another thing here that you can see, this 10058 is typically called program counter. It's a pointer that points to these instructions that if we want to execute this instruction, these are the address that is stores in these instructions. Okay, then another very important thing that if you see in Linux environment, we see this format called ELF format, is executable and linkable files. These are the file format used by Linux for both shared libraries and executable files. They have ELF format. There's something really interesting that is recorded in this ELF format. Now, for example, ELF format always starts with ELF plus 07F, and it's just a magic string that represents this is a ELF format. Then there are lots of information that is stored there as the header of this file. Just store the required information. So this format is predefined. So every program, every operating system, at least the Linux and Unix system, should follow this format definition. Even today, this format have been designed there for many, many years, but today everyone is still following this type of format. Now, even for GPU programs, they still execute this type of program. I just want to introduce one concept. When we talk about the GPU programs, we always talk about a concept called fat binary. Fat binary means this is a binary program that contains both the host program and the device program, the GPU program. Then how it's done is basically by compiling the GPU program into a EL file on its own. Then embed this part of EL file, the GPU EL file, as part of the host EL file. Then when we call that program, we just use some pointers to redirect to that point, then we can start to execute that GPU program. Okay, another concept here is called application binary interface. Then you may heard of API, application programming interface. That's how one program communicates with another program. Now API is the binary interface that how a program communicates with the hardware. And these are predefined interfaces, predefined format so that your machine can read. There are several tools that can help us deal with the ELF format. For example, there's a read ELF. Read ELF have many arguments that we can dump different parts of the ELF format. Hex dump is another useful tool. It's not related to ELF, but it can help you understand the binary format in the hex style. Okay, so let's see. You can introduce something. We can use the read ELF output to understand a little bit more about what's inside the ELF format. There's definitely something that you can learn on your own, but I want to just point out a few high-level things. For example, this is the header of the ELF file, right? As we see in the previous slide. Then it requires what's the type of the program, now what's the machine, now what's the ISA that this program is recorded. Then start of the program headers, section headers. So those are other parts of the EL file that it's pointing to. And the size of the headers and the section headers. Now, later on, we're going to talk about the sections. Okay, so section header table. What are sections? So the program, the EL file is represented with different sections, and the sections are represent different things. For example, text. Text are actually stores the most important part of the program itself, the instructions. Then you can see the flag here. It's at least you can see the X. This is the executable part, right? This X represents only this one is executable. Then RISC-V attributes are standalone for RISC-V. Now we don't talk about it. Symbol table, string table are special things. For example, string table records all the strings that your program requires. For example, when you print something that this request is failed, then we cannot process or program crash. This type of strings that are hard-coded into the program. Now, if you write a string that prints something, everything is stored in this string table. Okay, what is symbol table? Symbol table records all the symbols in this program. Now, what are symbols? Then typically at this stage, you can consider two different types of symbols. From here, you can see the symbols, although it's really small. There are two symbols here. One is start. This you can consider start is a special function. Okay, it's a function that you don't write. And another function is main. So the function name, all the function names are represented in symbols in your program. And another type of symbol is labels in your program. I'll just try to see, I think there should be one example. Yeah, this is a symbol table. You can see start and main are symbols, right? And there are other parts of the other type of symbols. There's no label here. Okay, so sometimes if you want to jump to a certain location, then those jump locations are also represented by symbols. Okay. Then now we talk about labels. We have talked about labels. Okay, is there a label here? No, there's still no label. Then this main Wayne's program is actually stored as a label rather than a function name. So your program, your assembly doesn't really know what is a function. So it's stored as labels. There are comments, and the most parts are instructions. So for example, here we can see these instructions as ADDI. ADDI are for integers. Then there's special eCall. eCall is an instruction that is calling operating system features. Then, for example, if you want to print something, if you want to allocate some memory, then those are all that you want operating system to provide some services for you. Okay, so for example, we define one as, if we define one as the print integer operation, then we store it into A0. Now X0 is actually 0. It's always hardwired to 0. We'll talk about that later. And this is actually a move operation that moves 1 to A7. Okay, just store it in A17. Now we store T2, whatever data is in A0. So this is a move instruction. There are actually both move instruction. I don't know why this one, this is disassembled in this way, but there are similar instructions. We're moving from T2 to A0. So eCall is an instruction without operand, without anything that we're processing on, but it follows some convention that we execute the system call number recorded in A7, and the argument is stored in 0. And in this way, we're printing Now, in this way, we're printing the integer in A0. Okay. So for example, here, system call 10, if we define system call 10 is exit, then we store it in 10 in A7. Then we don't really need an argument. Now we do eCall, and then the program will exit. Okay, these are something that our program can communicate with the our program, a user space program can communicate with the operating system. Now for every instruction, now we have mnemonic, that is the operation, or sometimes we call this part the opcode. Now, for example, this is an ADDI instruction. Now we have operand is the element that we're processing on. They can have sources and destinations. Then the convention is the first register, the first element is the destination, and the rest are the sources. Now we take this as input and we store it there. And here we see T0 and X0 are registers. They are registers that are storing the information for this program. We have T0 and X0. You have one that's an immediate number that is hard-coded into the program. So for most of the, for many numbers that we can directly encode these numbers into this instruction, the instruction will allocate some bits so that you can store some numbers. But sometimes these numbers is a weird number that is not some number that we can directly encode, because the whole instruction is encoded in 4 byte size. Okay, now one integer number can be 4 byte size on its own. So sometimes there's no enough bit to store here. Then these type of things should be stored in some other sections of your EL file so that we have the pointer to that point, then we can load it the time we need to use it. Okay, so here are the instruction format. Now we're not specific for RISC-V. Any type of instructions, any type of assemblies follow this type of format. Then we're going with RISC-V ISA and see how RISC-V ISA is organized. RISC-V is defined by UC Berkeley, then as the 5th edition of their RISC instruction set. Okay, then it highlights for extensibilities. For the base ISA, they only have RV. RV is RISC-V. RV is 32I integer and RV 64I integer instructions. So those are the basic sets, and they're really simple. They're designed to work even for the simplest machine. The minimum core can support this type of instructions. So there are some cores that are just there to, say, in industry control, like control robotic arm or something. It really does not need to be high performance, but really need low power and perform simple operations, or something, a core that executes in a remote sensor that it operates on battery. Okay, so they want a RISC-V core, a simple RISC-V core can execute on that type of machines. So they are intentionally designed to be minimum. But if you want to build with really high power cores with RISC-V ISA, yes, you can do that. Then you can use this type of extensions. Then you can, there are many standard extensions. For example, the M extensions support multiplication and division, atomic instruction, single precision floating point, double precision floating point. That means for a basic machine, you don't really need to support floating point operation, right? For compressed instructions, these are special instructions that have shorter instruction, shorter sizes. For vector expansion, then these are simply instructions that we can perform. We can calculate new instruction. We can calculate multiple numbers in one instruction. Then this type of extension set require extra registers. So it's really flexible there. Then bit manipulation extension, like bit level masking this type of operations. And it's really efficient at this level. Okay, so there are many, many extensions that you can add. Now you can also define your own extensions. For example, that people are using RISC-V to build CGRA devices. There's some devices we'll talk about later. Then there's also like a trend of using RISC-V to define GPU architectures. And then the GPU architecture definitely have a different programming model as CPUs, so their instruction set is not good enough. So they just add extensions to support this type of GPU operations. And so far at academia level, it's successful. They can demonstrate using something like FPGA to simulate a GPU implementation, a RISC-V based GPU extension, and they demonstrated it was possible. Okay, so when instructions, they're encoded in a 4-byte long sequence, then a instruction set need to define what registers are available. So how many registers are there in the default instruction set? Now you can see from X0 to X31, there are 32 registers. So if you really have a simple core, simple RISC-V core, each core has 32 user programmable registers. There definitely need other type of registers that storing other informations. For example, is PC even here? Yeah, PC is even not here. There are some other registers that are like structural registers that just required by the core. Like next time when we talk about the CPU architecture, microarchitecture design, we'll talk about those registers. Those registers are required to implement a CPU core, but user cannot program those things. So only these 32 registers are something that user is programmable. And we actually need to reduce this one because X0 is always 0. Then even if we write something into X0, it will stay 0. Okay. So they have different ABI names or assembly names. In assembly, you can either write something like 0 RASP, or you can write X1 or X2. Okay, they have different purposes. They are defined to be used in different ways, but these are more like conventions. So you better follow this type of convention if you want to work with other programmers and other programs. But if you really don't want to follow these conventions, in theory, yes, you can do that. You can just use as 32 different registers as just registers. Okay, now descriptions. Now we can see RA is return address, SP is stack pointer, there's global pointer, thread pointer. We're not going to touch that. And those are temporaries. Save the registers. It's a frame pointer. Function arguments. When you call a function, then you use A0 and A1 and A2 to A7 to store the function arguments, right? Now A0 and A1 are also used for return values, so that here you can use registers to return 2 values. And S2 and S11 are saved registers. We'll talk about what saved the registers later. And T3 to T6 are temporaries. That means T02 and T36 are something that you can just use to store some information there, without worrying that you are overwriting someone else result. So one thing you can see here, each core has 32 registers, right? That's a really, really small number coming from the GPU world. So how many registers are there in a GPU core? Let's just consider vector registers. For a vector register, for a GPU core, a vector register. So first of all, for each verb, how many registers that we can have? We can have 256 V registers, each verb. Okay, now each verb has 64, or wavefront, has 64 threads. Okay, that means for each verb, we need this number. Registers. What's the number here? What's the result here? for then this 16K registers, right? So 500 times larger than that one. This number of registers is also the number of registers that is associated with a wavefront pool and also a SIMD unit. So if you really fully use 256 registers in one warp, then that means this wavefront pool can only include one warp, right? Because these registers are allocated there. You are using all the registers, vector register. Vector registers are one limiting factor about how many wavefronts that a wavefront pool can handle. The key point is, I just want to tell you that the GPU really allocate a lot of resources for registers, while CPUs only have a very few things. That's why if you consider all this data is stored in registers, and if you want to store this data into the memory, it will take a very long time and a lot of energy. If you want to store 32 bytes of data, 32 register data, and each register is 4 bytes, okay? If you want to store 32 integers into the memory, it will take no time, no big problem. If you want to store all this data for GPU to the memory, it will take a lot of time. So that's why context switching for CPU is very easy. For GPU, it's almost impossible. That's why GPU can only support something like you just execute your whole warp until everything is done. Then you just kill it, then start another round, start another warp. For CPU, you can just execute a little bit, then store it back to a memory, then bring another context in, another thread in, execute it, and store back to memory. That's possible. Okay. Okay, what instructions are there? So for RISC-V, we can have logic instructions and or XOR. And there's a I and XOR I. What's the I there? I stands for immediate. There is one operand that is an immediate number. Okay, so those are bit level operations. Then there's shift instructions. For example, there's a shift left, shift left, shift right, and shift right. But why there are two shift right? Is because one is called just read the third letter. L stands for logic. A stands for arithmetic. Okay, what is logic? For left shift, no problem. Left shift always fill with zeros. The right shift has two different possibilities. You can shift either always shift zeros, always fill with zeros, or you can fill whatever data result is whatever bit that is represented in the first bit. Remember in two's complement representation, if the first bit is 1, that means it's a negative number. And if it's a first digit is 0, that's a 0 or positive number, right? So if we do shift right, then filling with ones, filling with the value of whatever that is in the first bit will maintain the value, okay, even if negative value will maintain the sign. So that's why we need two versions of shift right operations. Then we can have arithmetic instructions, add I, add with an immediate number, and sub instructions. So there's no sub I because you can just add I with a negative immediate number. Multiplication numbers are not in the RV32, but they have a similar format. I just want to mention, to perform one multiplication operation, 4 byte multiplied by 4 byte will result in what? Just consider 9 multiplied by 9 will result in 81, right? So one digit will result in 2 digits. If you consider 99 multiplied by 99, I don't know what's the value, but it's a 4-digit thing, right? So for decimal numbers, if we start with 2 digits, we end up with 4 digits. The same thing here. If we have 4 byte by 4 byte, we end up with 8 byte number, right? But remember, each register is 4 byte. That means we cannot really complete a multiplication operation in one instruction. We have to use 2 instructions to perform a multiplication operation. That's why here we have mut, which calculates lower 4 byte. Okay, here we have these 2. We typically first calculate mul, T2, S3, S5. Then at T2 here stores lower 4 byte. Then mul H, T3, this T3 stores the high 4 byte. Okay, 2 instructions to calculate multiplication operations. Now we need to talk about branching and how CPU handles branching. Now it's much easier than CPU here, but there's some ideas that are similar. We don't have the execution mask. We don't need the predicated execution. Now we simply, because there's one instruction, and we just either execute it or skip it. So here we add a conditional branch instruction, BEQ. There are some conditional branch instructions. BEQ, that means branch if equal, branch if not equal, branch greater equal, branch less than, branch greater equal unsigned integer, branch less than unsigned integer. Okay, there's some instructions. Let's just look at BEQ. BEQ means branch if it equals. If S0 and S1 equals, we go to the target point. Okay. So target, this you might look at like this is a string, right? In assembly, this is a string. How it's encoded in binary is basically either by an offset of the address. So here there are 2 instructions in between. So this may probably be 2, or it can be a absolute address. Just directly say, oh, the address of this instruction, then you can jump to that point. Okay, the target, although it takes a line in assembly, it doesn't really take any addresses because this is stored in a separate symbol table. So in the text section, these are just encoded one instruction by one instruction. These are exactly 4 bytes away from the previous instruction. Okay, so here, if consider S0 equals to S1, they're both 4. If they equal, what do? Is we call this branch is taken. The branch, by the way, branch can either go back or go down. Okay, so in this case, branch is taken. Taken means we'll take the branch, then we'll jump to the target. That means these 2 instructions are skipped. Then we don't even consider these instructions. When branch is taken, then we directly jump here, we execute this line. Now, when branch is not taken, we just go down, we just execute one instruction by instruction. Then just remember, you see this code, we do something, then after that, we also do something else, right? If we do something else, this is add instruction is the something else that we're executing. Something else we're executing. So in assembly, it's executed in a for through style. So there's no if else, there's no branching. It just, if you, well, I cannot say there's no branching, there's no if else statement. We just directly go through instruction by instruction. Okay, if you really want to go somewhere else, just add a branch there. Okay, this is on the flipped condition. The only thing is the only difference is there is BEQ. On this side, we have BNE. Then BNE means branch is not taken. So we just go, and we'll execute this line of code, and add, finally add. This add instruction are executed anyway, always executed. You can use this way. And you can see the pointer on the other side. Okay. This branch is not taken. So there's another type of instructions. Here we're talking about conditional branch. So when the condition holds, we jump. We go to another location. Another case is we do jump no matter what. This is called jump instructions or unconditional branch instructions. And here we can either just directly jump to a label or jump to something that is some address that is represented in a register. For example, if you want, this is represented by a either a redirection table or a function pointer. So sometimes in C program, you may do something like a function pointer, but sometimes you may do like a switch case. In switch case, you may just say there's a table, right? If this is a case, this is the address that you want to jump to. It's another condition, this is the address you eventually want to jump to. Then this address is stored in a register. So last time we also talked about this concept called basic block. And what is a basic block? A basic block is a sequence of instructions that are always executed together. So there's only a single entry point and a single exit point. These 4 instructions is one basic block. There's 2 instructions is another basic block. And this instruction is another basic block. Okay, so because these instructions are always executed together, so we sometimes just consider those as a unit of scheduling. Okay, now when we consider either compiling or sometimes performance modeling, then we just model at basic block level. Let's skip these examples. Those are if statement, if else examples. Then switch is done in this way. So case 1, right? Case 1 is a label, and we do something. Now eventually, when we're done with this case 1, we jump to a certain location. Right? There's also a default. So there's always a jump to the done operation. That's why we need to have a break in C program. So C is designed to be really close to assembly. That's why it just, if there's some instruction, then we need a break operation. Otherwise, it's falling through. Then some newer languages like Go, they just remove this feature. They never fall through. So fall through is really not intuitive to humans. Sometimes it's very likely to be the source of bugs. Okay. Now, while loop, let's just spend a little bit of time talking about loops. And we never talk about assembly for GPU loops, right? But in CPUs, we can see how loops are implemented. And this while we just write this label in the same line as this instruction, okay? But if you write in a separate instruction, it's exactly the same. So what we do here is at the beginning of while this loop, we consider if S0 is equal to T0 or not, right? When they equal, so there's a implicit flip of this condition. Then when we write the program, we say while it doesn't equal, right? Here we check if it's equal, then we just directly go out. We flip the condition. Now when these 2 numbers equal to each other, we jump to done. And we exit the program. Otherwise, we stay in it. We just go down to the real calculation, then we jump, right? We jump back to BEQ so that it will stay in that loop and keeps executing. Array access. Now, I think last time we talked about array access in GPU, then we will skip this part. Okay. So binary format. By the way, so last year, when I talk about the RISC-V architecture, I spent 2 lectures to talk about this whole session. Then this lecture, 2 lectures for what we covered today. And this year, I really want to squeeze it to 1 lecture so that we can cover something more useful. So, but we really need to talk about this part because next time when we design the core architecture, we need to understand what type of instructions are there, why we need this type of instructions. Then, so we can design the circuit directly for this type of instructions. So there are different type of encoding. So we encode different instructions in different ways because there are only 4 bytes to encode 1 instruction. So the resource is really tight. So we can only use this limited bytes to represent instructions. There are a lot of instructions for us to encode. So let's look at what instructions are there and what formats are there. There are basically 6 types of instructions. We'll go one by one. And they also looks very weird. We'll explain why they are designed in this way. So the first type is the R type. R represents for register because all the operands are registered in this case. So typically we consider in this way. We consider op func7 and func3 as one unit. These are the opcode. These are bit that represents what instructions, what operations that we want to process. So the op plus func7 and func3 combine to encode add instruction. Okay, so you think how many bits are there to represent this instruction? There are 7 bit, and 3 bit. There are 17 bits. That's actually a lot, but not all the 17 bits can be used because these ops are limited. We need to reserve some ops for other type of instructions. Okay, so but 17-bit for this type of things, and if you consider 2 to the power of 17 or 2 to the power of 16, that's actually a lot of instructions. 2 to the power of 16 is 64K, right? Now, don't expect hardware can support this number of instructions. The largest number of instructions is what I see in AMD GPUs can support something like 2000 type of instructions. There are many instructions that are just slight different variations. So for RISC-V, we can execute say 100, 200 instructions. That's already quite a big set for CPUs. But anyway, so those bits encodes what operations that we want to perform. And we even the RV32I and RV64I are not really using all the bits there. They reserve some bits, and they reserve some code for the multiplication, division instructions. But here, these are the examples. For example, ADD S2, S3, S4, right? So here, we use number 51 to encode ops for ADD and sub. Then here, this 32, if you consider 32, it's actually only 1 bit is changed, right, from 0. So only 1 bit is changed from add instruction. Then, so we from this func7 and func3 and op, we know it's add and sub instruction. Now RS2, RS1 are the different values here. Now you can see those are encoded in this way. Now, for example, source, this is source 1, source 2, right? 19, then we directly write number 19 here. 20, we directly write number 20 there. Although eventually we need to convert to binary, but these are number 20 in decimal format. Now here, destination, RD is for the register destination. We simply write number 5 here. Sorry, number 18 here. This is why we have a second representation rather than S2, S3, S4. S2, S3, S4 are more human-friendly. There are 4 different series of registers. But eventually, we just write X18, X19, X20. Those are more machine-friendly. That is easier to encode. Okay, so this part and this part have no difference. But on the right side, on the machine code, we have the binary representation. Okay, so our registers are the most easy to understand. Okay, let's go with the next group. So by the way, this is a table for all the instructions in the RV32I table. This is like a cheat sheet. If you want to write something like super simple core in Verilog, or if you want to write emulator, then you can just look at this cheat sheet. And it's rather easy for you to write the disassemble the instructions. Okay, so this group are the R-type instructions. There are only 10 instructions in the RV32 set. Add, sub, shift left, XOR, shifted right, or AND. These type of instructions support this format. And you can see the ops are all the same, okay? Then this part are slightly different. On this part, there are only one bit can change. Okay, only 10 instructions here. So let's talk about I-type. I-type are very close to R-type. They just replace one. It just replace one operand with the immediate representation. Okay, so op is still op. It can be different from R-type. Then it only have a funct 3, so it doesn't really support that many instructions because it needs to reserve space for immediate values. So what's the immediate value here? It's from 0 to 11 bit. So there are 12 bit that can be used to encode the binary, the immediate value. So you cannot really encode a very large immediate value. The range is limited. Okay, so here we have some examples. For example, ADDI, we have number 12. That number 12 is stored here. Then RS1 is 9, that means X9. RD is 8, that's X8 register. And func is 0, op is 19. Okay, remember 2's complementary representation. If we need to represent number -14, then we use this special way to represent 14, -14. Okay, so not many instructions here now, but in general, it's very similar to R-type. So from here, I want you to reflect why RISC-V encoding is designed in this way. It's designed to be really machine friendly. So it doesn't really want a very complex decoder. It wants to be consistent across types. So if you look at here, the low 7-bit are always ops, right? From this way, 7-bit are ops. Then 5-bit are RD. 3-bit are the function there. Then 5-bit are RS1. Then only this part is different. The whole thing at this part is the same for R-type and I-type, right? So for R-type, here, the 3-bit is RS2. This is R-type. Then for I-type, then we don't have RS2. Everything is immediate number. Then for this 7-bit, we have funct 7. Okay, you just want to keep consistent across different type of encodings so that decoders can be decoded rather easy way. So this makes sense because you're not going to read the binary code anyway. It's machine who will read the binary code. So the binary code needs to be machine friendly, not human friendly. Question? When they're decoded, now we'll talk about that next lecture. This core design, but but I can give you a quick preview about how this part decoding is done, right? Decoding decide 2 things or even 3 things. So if you look at, say this is the register file, right? So there's some control logic needs to go into a register file, say which register we need to read. Okay, if you consider register file in this way, then this is one register, this X0, X1, and so on, right? Then eventually we need this thing called ALU. Then how we can define which one fit into this ALU multiplexer, right? So all of them are connected to a multiplexer that fits into one ALU. Another multiplexer here. All of them are connecting to both of the multiplexers. We need selector bit to decide who can go through this multiplexer. Then ALU also can perform add instruction, sub instruction, multiplication instruction, many instructions. So what instruction needs to be performed there is also controlled by a control bits to decide for which operation that we need to take. And actually, if you don't consider power gating, the annoying thing about ALU is it actually works in this way. So these two are connected to say add unit. Okay, it can, if you also have a multiplication unit, so add unit and sub unit are the same thing. Okay, they share some unit, but they still need extra bit to decide if it's add or sub operation to toggle that which type of operation that we're considering. It just needs extra bit to go into this combination logic. And there's a multiplication operation. There can be shift left, shift right, by shifting operations. Then the annoying thing is they go to all of them. Then eventually there's a multiplexer that select which result that we want to use. Then this multiplexer also need control logic, decide which one, which result is eventually selected. Then go back to the register, and eventually when to go back to the register for writing, right? So this is the other way of the multiplexer to select which register that we can write into. This also requires decoding process. The decoding process need to parse this format to decide these control bits that controls the rest of this, the back end of this pipeline. It's something that we're going to talk in next lecture. Okay, let's just quickly go through other formats there. S and B type, for example, S this S type. S stands for store, so we store the data to the destination. I think we can quickly skip this part because you can read the document. There's something more important there. And this is B type. Something that when you read the technical documentation, then you can understand how it works. I want to focus slightly more on how functions are handled. Why the registers are temporary registers and stored registers, different type of registers. So we have an example of function. Then a function has a function header. We have return values and input arguments, and the operation that we're doing here, and the return. I don't know where I find this screenshot. I don't know why this return has a parenthesis there, and this is not good C syntax. It's not wrong syntax, it's just not good. Return is not a function call, return is a statement, right? So, but anyway, it returns the sum operation, then it returns something. This is C definition. In some other language, we can return multiple values. So this is a function. Now, how this function is encoded into a CPU program in assembly, then we need to understand the concept called stack frames, right? So when we call this function, we grow a stack frame. Now, if we call another function, we go another stack frame. When we return, we decrease a stack frame. So how these stack frames maps to assemblies? Now we can look at how assembly works and how assembly deals with registers, how assembly can handle these arguments and also the return the value. So I just want to quickly give you some arguments, how we handle arguments. We can use registers to handle arguments. Okay, so this is something that is defined by a calling convention. A calling convention is defined jointly by the ISA, the operating system, and the compiler, the program language and the compiler. So all of them can decide like which type of calling convention that we can use. And if you say C language working on Linux may have a calling convention, but if your compiler really want to develop some new calling convention, it should also work in general. So this is a RISC-V calling convention. Then let's start with a simple function that doesn't do anything. What we do here is when we call, we use a jump and link operation. The jump and link is doing two things. It jumps to simple, this label, right? Simple is here. It jumps to this point and start to execute from there. But also, we need to know where we're jumping from, right? So that we can return to that location. It's not randomly return to any location. So we can return to the location. So JAL is performing the other operation. The second operation is to store the current PC, actually the PC plus 4, the next instruction. Otherwise, we're going to execute this function call again. It will jump to another location, say PC plus 4 into RA. So whenever it's doing PC plus 4, it involves some ALU operations there. Okay, so it stores PC plus 4, and then we jump there. Okay, then this simple, if it's a return, then we don't need to do anything. We simply jump back, jump and return. Then we return back to the original location. So JR here is jump by register. So the RA is the register storing the address that we're jumping to. Then when we have arguments, how we deal with argument. So look at this example. We have FGHI, and F plus G minus H plus I. Okay, we need to parse 4 arguments, and there's one return argument. What we do here is we store them in A0, A1, A2, A3. Right, those are the arguments that we pass. Now here, what we do here is we do the add instruction, another add instruction, R-type instructions, and we do the sub instruction. Then eventually we do this, add A3 0 into A0. So for most of the time, if we hand write an assembly, we would typically write MV instruction, move instruction. And we typically write move A0, S3. Okay. Move whatever in S3 to A0. Then, but if you consider the effect, a move instruction has no difference with adding 0 and storing it into another address, right? So to save one instruction, there's no need to have an encoding for move operation. They simply use add to replace. Okay, but if you hand write this instruction, the compiler or the assembler can also recognize this instruction and can compile into and can assemble into that ADD instruction. If it's a disassembled, it will disassemble into add instruction. Okay, so this type of instruction is called pseudo instruction. So instruction does not exist, but also exists somehow, exist by convention. But anyway, here, this is a move instruction, just move to A0. Then we jump back to this location, and we continue to execute this add instruction. However, there's a problem. The problem here is this S3 is a special instruction. So if the main program use S3 here, then use S3 after this point, the S3, because the S3 is modified, then the context in this main function is not maintained, right? So the problem is this S3 is being modified. Remember, S is a stored instruction and is a callee, it's a caller maintained instruction. See here, S instructions are saved instructions, saver, who should save it? This callee should save it. Or who is using it is the caller, right? The main function is the caller. The diff of sum is the callee. So the caller is actually using it. So caller will assume that this value is not changed. Okay, so that's why we cannot modify it. We cannot modify here if we're following the RISC-V convention. We cannot modify this value. So what we can do here is if we really need this register, we can store it in memory and recover it from memory before we return. Okay, so that the context of the main is maintained. It's not changed. So by the way, remember T are temporary zeros, temporary registers. They're temporary registers. That means the callee can change it however they want. The caller should not expect they are consistent. Okay. Right. So they can modify it any way they want. And then the caller cannot really expect that they have the same value after this function is called. So at3 is a problem here. So what we do here is a more conservative method. We form a stack frame. How we form a stack frame? So consider there are several values that are useful, right? For example, we have at3, T1, T0, and T1. Those are the values that we're going to use in our main program. We need to use T0, T1, S3, right? We need to use these three registers. What we do is we first store whatever in at3 to SP, the stack pointer, by 8, right? Offset 8. What we do here is we grow the stack, make the space on stack to store 3 registers. So we change the stack pointer value. We decrease by 12. That means we're growing the stack. We're allocating some space. Okay, stack are a piece of memory that's always considered being allocated, but there's a fixed size. You cannot allocate too much element in stack. And we add this number. So we grow the stack. We allocate some space. So that's why this part of allocation is really fast. That is much faster than malloc. If we can save something on the stack, we should save something on the stack. We should avoid the heap. If we use heap, use malloc, it's stored on the heap. Question? These are nothing special. It's just a part of the memory, main memory. It can be cached, but if it's cached or not, we don't control. So these are not hardware-specific memory. It's just regular memory that, say this is a CPU, then we have on the motherboard, we have those third-party DIMM memories. Then we just insert there. Okay. So stack memory. Then we store this data we store this to at3, store this to store T0 to this part at the stack, store T1 to the stack. Then we perform the regular operation, right? The regular operation is performed here. Then before we return, what we do is we recover the context for the main program, for the caller. So we just basically, we load data from whatever that is stored on the stack, then we save it back to at3. Okay, we save this to T0, we save this to T1. Okay, this is a context recovery process. So I have to say this is, in general, this is not how RISC-V should handle things, because we have T0 and T1, right? T0 and T1 are assumed to be maintained by the callee. So callee can modify it however they want. right? That actually save some operations, save some load and store operation. Load and store operations can be expensive. So we want to reduce this thing. So in fact, we can simply remove this and remove T0 and T1 and keep the stack frame to be only one register that works. There's a more RISC-V style stack management. Okay, some commonly used data can stay on the stack. Then, as you may notice, this is too conservative, and we can simply use the stack to hold S3, right? This is the RISC-V style. Then it can reduce some, if it's a small function, then we can reduce the load and store operations there. Now we can even do something more aggressive. Basically, we have A0 there. Then A0 is the A0 and A1 can be used for return value, right? And in this case, we can directly write the result into A0 and just eliminate S3, no problem. Now it just really depends on if the compiler is not smart enough to use this type of code or not. And this is a really small example. When there's a really complex example, probably you just do not have the chance to do this type of operation. Right? Sometimes your stack frame is really large. If you write something like int A 4096, then all these 16K data are actually in the stack. Okay, it's a statically allocated part of data. Then you hard code this number there. Then this data are on the stack. This definitely cannot be handled by register. The whole thing is handled by the stack. Okay. Okay, so when we talk about non-leaf functions, then there are some registers the caller need to save. Now, when we call these functions, if the caller have been using T0 to T7 and A0 to A7, they have to save it into the memory, then recover it when they need to restore the value again, continue to use the value again. Some registers are callee to save. For example, S register RA, the callee need to save this type of registers. Okay, now another thing is the stack grows and shrinks. When we call a function, and we grow the stack to store this type of information temporarily so that we can recover later. Another thing is called register spilling. So sometimes the register is not enough to handle the data, that handle the variables required for whatever that we need to store in the register. For example, if you have a lot of things like this, ideally you want to store all the variables that your function need in the register, so that is really fast, right? However, on CPU, on RISC-V CPU, a simple core, you only have 32 registers, and many registers like RA, SP, there's something that you cannot use. There are only a few registers you can use. So when the register is not enough, you have to use stack memory to manage those variables. And whenever you need to use it, load it back to the register and start to do the calculation. Okay, it's called register spilling. Now for CPUs, register spilling are kind of expected because the register space are so small. You don't have so many registers that you always spill. But on GPU, this is something that we should try to avoid as much as possible because you already have so much register space.